Okay. So yeah, good morning. This is the third IGRAC meeting. My name is Brian Robertson, manager of supply resource planning and representing Intermountain. And this is September 17th. So we'll go ahead and do introductions first. I'll just go down the line. So Bruce Folsom.
Yes, Bruce Folsom, tinkering with my button. Good morning. I'm a consultant with Brian and his team.
Thanks, Bruce. Kathleen.
Good morning. I'm Kathleen Campbell. I'm a senior engineer with engineering services for Intermountain Gas.
Thank you. Ginny.
Good morning. I'm a resource planning economist on Brian's team at Intermountain Gas.
Thank you. Ryan.
Hello, I'm a resource planning economist representing Intermountain Gas.
Thanks. Matt.
Matt Hunter, President and CEO of the Pocatello-Chubbuck Chamber of Commerce.
Thanks, Matt. Darcy.
Good morning, Darcy Nagum, Vice President, Energy Supply with Intermountain Gas.
Thanks, Darcy. Mike.
Good morning, everyone. This is Mike Parvinen with Intermountain's regulatory team.
Thank you. Rebecca.
Good morning. Rebecca Wildman. I'm with Business Plus.
Thank you. Chris.
Good morning, Chris Robbins, Director of Gas Supply and Control for Intermountain.
Thank you. Mark.
Good morning, Mark Sellers-Vaughn, Upstream Resources Manager, Special Projects with Intermountain.
Great, thanks. Sungjay.
Good morning, everyone. I'm Seungjae. I'm engineer in PUC.
Thank you. Zach.
Yep, Zachary Sowards, Senior Engineer with Engineering Services with Intermountain.
Thank you. Bailey.
Good morning, I'm Bailey Steves. I'm an economist on the resource planning team with Intermountain.
Vicky.
Good morning, I'm Vicki Stevens. I'm with the Idaho PUC.
Eric.
Good morning, Eric Wood here, gas supply manager at Intermountain.
Thank you. And I think I see Kimberly jumped on.
Hi, I'm Kimberly Loscott. I'm a technical analyst at the Idaho Public Utilities Commission.
Great, thank you. And I don't see anyone else, but if anyone jumped on and I'm not seeing your name, please feel free to introduce yourself. Okay. So I'll discuss the feedback process here in a little bit, and then we'll discuss the agenda for today's presentation. So just a reminder, everyone, you can email us at irp.comments@intogas.com with any feedback. We do appreciate feedback sooner on in the process. It helps us be able to incorporate it into this IRP. So if you can get it done within 10 days after this meeting, that would be appreciated. We also have our website. I'll find the link to the website, but out on our website, you can find the presentation, the meeting minutes, and the video recording of previous IGRAC meetings out on that website. So for the agenda today, I've done the welcome and introductions. I'll do a quick safety moment, and then Ryan will hop in and discuss the load demand curves, and then Kathleen will provide a capacity enhancements presentation. and then I'll discuss resource optimization. And then we'll open it up for questions, discussion at the end, but feel free to ask questions throughout the presentation. You can raise your hand, you can just come off mute and interrupt us, or you could put in questions in the chat. We'll monitor the chat log and try to answer questions that way as well. So yeah, this is a little bit of a flow chart to kind of give everyone a background of the IGRAC presentations and how they all kind of feed together. So in the first IGRAC, we discussed the economic overview, our residential and commercial customer growth, the design weather, and then the industrial demand and how all of that leads to our demand. And then we discuss in IGRAC 2, what's highlighted in blue, the transportation capacity and storage, natural gas supplies, traditional resources, and energy efficiency, as well as our residential and commercial usage per customer that comes from our CMM model. So that left, that leads to our demand, and then the right leads to our supply and deliverability. So in this meeting, what we'll discuss is the overall demand, the load demand curves, and then how we optimize those, utilize those to optimize our upstream resources as well as our distribution system planning. So like I mentioned, I'll do a safety moment. We like to include a safety moment during all of our IGRAC meetings. So right now is kind of storm season. So you'll want to make sure that you are protected from lightning. Make sure you seek shelter and stay indoors when there is a lightning storm. Before the storm, make sure you look for, if you're planning any outdoor activities, make sure you look at the weather. That way you're not stuck outside in a storm where you can't seek shelter. Make sure lightning safety, you have that as a plan. Unplug electrical items to avoid power surges during a lightning storm. And then make sure you bring your pets indoor. During the storm, again, avoid seeking shelters in sheds, picnic shelters, covered porches, tents, or under trees. Avoid high ground, open spaces, and trees. Stay away from metal objects. Keep clear of doors. Plumbing can conduct electricity, so wait until the storm passes to take a shower. And then if fishing, return to shore and seek a safe shelter as soon as possible. And after the storm, so charges of lightning can linger in the clouds, so make sure you stay indoors at least 30 minutes after it's cleared up. Okay, and now I will pass it over to Ryan to discuss load demand curves.
All right. So in this section, we'll be going over the load demand curves for the total company and areas of interest. Next slide, please. And the key variables that make up load demand curves are forecasted usage per customer per degree day, forecasted customer counts, and in addition to a base case, we also put together a low customer growth and high customer growth scenario. This was discussed in IGRAC 1. Design weather conditions. This gives us the forecasted HDDs to use for peak events. Demand side management, and this is a projected reduction in demand from increases in efficiency. This was discussed in IGRAC number 2, and the maximum daily flow quantity for our large volume customers. Next slide, please. This slide is just a diagram that highlights the load demand curve methodology. So on the top row, you can see this equation is the product of usage per customer per degree day, customer count, and HDDs, which gives us the residential and commercial total daily usage Then we take that and subtract out the demand side management and then add in the large volume maximum daily flow quantity to get our total daily usage. And this is what the load demand curves represent. Next slide, please. So as mentioned, these represent the forecasted daily gas demand, which uses weather normals, design temperatures, customer counts, and the usage per customer forecast. These help us ensure that we have proper capacity and are able to identify any shortfalls. These also help us measure the total company demand to ensure we are properly planning for our upstream capacity. And they are based on current resources and resources that are scheduled to be available during the planning horizon. Solutions to any shortfalls or constraints will be identified later. And they also help us with our storage management with things such as the amount of storage needed and planning around cycling requirements that some storage facilities may have. Are there any questions so far? All right, next slide. This is the 2025 load demand curve for the total company. And note that this includes the threshold for the maximum transport deliverability, which differs from the slides coming up on the areas of interest that show the maximum physical deliverability. We see that the peak day demand is forecasted to be about 536,800 decatherms, with the maximum transport deliverability with LNG, which is the dashed red line. Currently, that is 534,905 decatherms. So there's a peak day shortage here of about 1,900 decatherms. And the maximum transport deliverability without the LNG, which is the dashed blue line, is currently 479,405 decatherms. So there's a peak day shortage here of about 57,395 decatherms. Okay, this is the 2030 load demand curve. We see that the peak day demand here is about 582,518 decatherms. This is 8.5% higher than the peak day in the 2025 curve, which is an increase of about 45,718 decatherms. So in this scenario, the maximum transport deliverability with LNG peak day shortfall is currently 47,613 decatherms, and the peak day shortfall without LNG is currently 103,113 decatherms. Next slide, please. Next, we look at the load demand curves for the areas of interest, and here's just a reminder of what those are. And for these, we will present the same sort of overview for each of them, and note that the maximum deliverability lines that we'll see in the graphs will be the same for both the 2025 and 2030 load demand curves that we present in this section today. Next slide, please. Here's a 2025 load demand curve for the Idaho Falls lateral. Note that this area of interest has an LNG storage option located in Rexburg, which differs from the other areas of interest that don't have this option. Peak day demand is forecasted to be about 93,782 decatherms. Maximum physical deliverability with LNG, which is the lighter dashed orange line, is currently 110,200 decatherms. And the maximum physical deliverability without LNG, which is the darker dashed orange line, is currently 103,700 decatherms. So there's no projected shortfall here. Note that in the previous IRP, the maximum physical deliverability was 83,900 decatherms, which would have resulted in a projected shortfall, but there were upgrades to help meet this demand. Next slide, please. Here's the 2030 Idaho Falls lateral curve. We see that peak day here is about 101,425 decatherms, which is 8.1% higher than the peak day in the 2025 curve, increase of about 7,643 decatherms. Again, no shortfalls projected in terms of the maximum physical deliverability, but this one without the LNG option is close. Next slide, please. Here's the 2025 curve for the Sun Valley lateral. Peak day is about 20,735 decatherms. Maximum physical deliverability is currently 24,750 decatherms. Again, no shortfalls due to the upgrades made. In the previous IRP, the threshold was 20,000 decatherms, which would have resulted in a projected shortfall of 735 decatherms. Next slide, please. Here's a 2030 load demand curve. Peak day here about 21,693 decatherms, which is 4.6% higher than the peak day in 2025. This is an increase of about 958 decatherms. Next slide. Here's the 2025 curve for Canyon County lateral. Peak day here is forecasted to be about 109,018 decatherms. The maximum physical deliverability is currently 139,000 decatherms. Again, no shortfall due to upgrades made. In the previous IRP, the threshold was 103,200 decatherms, and this would have resulted in a projected shortfall of 5,818 decatherms without those upgrades. Next slide, please. Here's the 2030 load demand curve. Peak day here is about 121,529 decatherms. This is 11.5% higher than the peak day in the 2025 curve, which is an increase of about 12,511 decatherms. Next slide. This is the 2025 load demand curve for the north of state street lateral. Peak day demand is forecasted to be about 81,770 decatherms. Maximum physical deliverability is currently 82,000 decatherms, so no shortfall is projected, though it is very close, as you can see. And note that this slide and the next one differ from the slides that were sent out recently. We had originally included the upgrade in 2025, but it's not anticipated until 2027. Next slide, please. Here's the 2030 load demand curve. And peak day here is about 88,074 decatherms. This is 7.7% higher than the peak day in the 2025 load demand curve, which is an increase of about 6,304 decatherms. And notice without the upgrades, this would result in a projected shortfall of about 6,074 decatherms. Next slide, please. This is the 2025 load demand curve for the central Ada lateral. Peak day demand is forecasted to be about 79,120 decatherms. Maximum physical deliverability is currently 87,000 decatherms. So no shortfall again. In the previous IRP, without the upgrades made, the threshold was 74,500 decatherms, which would have resulted in a projected shortfall of 4,620 decatherms. Next slide. This is the 2030 load demand curve. See, peak day here is about 85,269 decatherms. This is 7.8% higher than the peak day in the 2025 curve, which is an increase of about 6,149 decatherms. Next slide. Are there any questions? Okay, I see a hand raised.
Yeah, I'm Seung-jae. Yeah, I have a quick question about your analysis. So your analysis is based on the base customer growth. That is right?
Yes, the base case.
Is there any analysis for the high customer growth?
Brian.
Sorry, what was the question?
I think he's asking. Oh, sorry, go ahead.
Yeah, is there any analysis per high customer growth?
Yeah, so we do the high and low customer growth forecasts on these, but generally we use the base for our modeling around the distribution system plans. But yeah, we can put together slides for the high and low. We haven't put them together for this presentation, but we can put them together if that's something you want to see.
Okay, yeah. And yeah, is there any sensitivity analysis for the key variables? Yeah, there are so many variables on there. So Is there any sensitivity analysis?
I mean, we have the high and low growth. We do different sensitivities around DSM. So we have 4 different DSM models that we model. But ultimately, at some point, you have to narrow down to the case that you find the most expected, which is the base case. But yes, so yeah, we do look at different models, different sensitivities, high, low growth, different DSM. In terms of like distribution upgrades, I know that Kathleen will discuss upgrades and kind of alternative options to those upgrades. So we consider alternative sensitivities around that as well.
Okay, yeah, thank you.
Thank you. And now I will pass it off to Kathleen if there's no more questions.
All right, well, I'll get set up. I'll do my own slides.
Sounds good.
Yeah, let's check. Can everyone see my screen?
Yeah.
Okay, thanks. I was gonna assume yes. But yeah, so I'm Kathleen. I'm gonna present today, and Zach's actually gonna present also. And we're gonna present on distribution system enhancements. So we'll get going. So this meeting, we got really set up nicely in IGRAC 2 for what we're going to cover today, because we're going to get into the projects, which is kind of the fun part, or I guess probably what engineers think are fun. But yeah, in IGRAC 2, we covered, just as a reminder, so we covered our system dynamics, our synergy modeling process. Oops, I hit the wrong button. Our identification of system deficits and constraints, and our distribution enhancement options. So this really set us up. So we kind of got the basis of what we're going to talk about today. And then along with that, we go into like our enhancement considerations and then how they're selected into the 5-year budget. And all that was covered in IGRAC 2. Okay. Oh, there we go. Sorry, I'm having a little bit of issue. It's just slow. So this presentation, like I said, it's going to support us up, set us up for the projects that are needed to support core growth. We're going to go through our alternative analysis, if it hasn't already been covered, and I think there's one that has been covered, but I'm going to briefly cover it a little bit on how we made that selection, or just a little recap of the previous considerations. And then we're going to talk about timing, cost, and capacity gained for each reinforcement. And then we're going to cover projects over $1 million today, is kind of the threshold for what we talk about. So just as a recap, I'm just going to go through our areas of interest. So for Idaho, we have 5. And they're shown here, and I know Brian went over this, so I'm going to keep it pretty brief, but we have the Canyon County AOI, which is kind of the Napa area. This is kind of the high pressure network that serves the expanding area of Napa, which is west of Boise. And then we have 2 kind of in the Boise area. We have the Central Ada County lateral and the North of State Street lateral. So just high pressure throughout Boise to serve all the demands in Boise. We got industrial, development, things like that. So lots of high pressure networks that are kind of interwoven through Boise. With that, we also have the Sun Valley lateral that runs up to Sun Valley, Idaho from Twin Falls. And then we have the Idaho Falls lateral, which goes from about Pocatello up to St. Anthony's. And then any area that's not in an AOI that's defined, we call them our other AOI. So all our other customers are in the others, and we have a couple projects for those too. So other AOI, so I'll just start and we're going to go through each one. So our other AOI is what I'll start with, and these are the reinforcements required to meet our 2030 growth predictions. So we have one that's called the Caldwell reinforcement, and this project's going to run on Chinden from Prescott Lane to Middleton Road. And it's being driven by a Idaho Department of Transportation upgrade. They're going to make this road 5 lanes. So just all the growth going on in Napa, Boise area. This is a planned IDT project that's planned for 2027. So we're going to run some 6-inch plastic in this area to kind of loop our system and then get in, before it's 5 lanes. So when things go to 5 lanes, there's lots of restoration cost and or just moratorium cost. So it makes the cost burden really high to get infrastructure in. And there's already lots of infrastructure planned. I heard there's a Fred Meyer's planned right now and a Winco for this area. So with that, you're just going to get subdivision growth, and probably some other commercial like strip malls and things like that. You'll need gas infrastructure for that. And that project, I got cost over here, so sorry about that. So it is currently 3.65 million, and that'll just support that future growth we're talking about in the area. And then there's not really an alternative. Like I said, when there's a road being expanded and we can get in kind of when it's being planned, it's the lowest cost alternative and it'll loop our system. There isn't really a comparable alternative. Just with the new infrastructure, we're going to need infrastructure anyways here. So when we can loop and, further reinforce our system, it just makes sense. And there's just not a comparable alternative. And the next one I got, this one is the new Plymouth Gate upgrade. Sorry. This is just a gate upgrade and it's planned for 2027. The cost is 3.64 million. And this has been discussed in previous IRPs. I know it was in the 2023 IRP. Just with timing, I think we've been assessing it, keeping an eye on it, and now we're predicting we need it by 2027. So just been watching growth, and we've adjusted timing accordingly. But this is just a gate upgrade, and there's not alternative because we basically have infrastructure already, connected at this location. We're connected to Williams, and it's connected to our distribution system. And it's just physical capacity. So a gate upgrade, you just need to upgrade pipes, components, and facilities to get the, that are undersized to get the, required, growth flow that you need. So that's other, and now we'll move on to our next AOI we'll cover, which is Canyon County AOI. This AOI requires no reinforcement to meet 2030 IRP growth. And this will be a recurring story you'll see, but we had done a significant project back in 2024, and that's our AOI update. But we had done USTIC Phase 3, and USTIC Phase 3 was 4.1 miles of 12-inch high pressure. And as the Phase 3 kind of implies, it had tied in 2 other 12-inch phases down USTIC. So USTIC actually has 12-inch high pressure from Star Road all the way past I-84. Which was kind of a long-term planning reinforcement. So that was the final phase that completed it. So with that, there's, with this IRP review, we did not need another project for Canyon County. We're able to meet growth with the system that we have currently. And next up is State Street Lateral AOI. So this one does require a reinforcement. We're looking at a couple projects in 2026 and 2027 to meet the IRP growth predictions. This project was also discussed in the 2023 IRP. And I'll just go through what we looked at, but it's capacity limiter. And I have another slide that'll show this a little better, but we have 12-inch high pressure on State Street and 4-inch high pressure on Linder. That's just undersized. We call it a bottleneck. So a bottleneck just means it has so much demand or it has so much flow that it causes velocity to spike, and we just lose a lot of pressure loss. So we just don't get the amount of flow we need down it, we lose a lot of pressure, which then compromises our system. So that's kind of the capacity limiter. So when we looked at this, there was a couple alternatives considered. And off the top of my mind, I believe it was just running pipe. But I'll talk, because we actually chose the uprate, so I'll kind of jump ahead. But and uprates kind of depend on what's feasible with pipe and records. But this one, typically, if an uprate's feasible, that can be your lowest cost solution. And it worked out for this one. Instead of running pipe, we can take it out of service and retest. And part of this project will be installing some plastic pipe to allow us to take the high pressure out of service and retest. So that's the State Street Phase 2 uprate. That'll happen in 2026. And then with that, we also have the State Penn gate upgrade, which is a little bit upstream and actually ties into the State Street Phase 1 uprate. But that gate's also going to need to be upgraded. And kind of like I said for the new Plymouth gate, this gate, there's not really an alternative to a gate upgrade because we're already there connected to Williams, and we have our infrastructure downstream. So we just need to go update the capacity of the gate, increase piping, increase components, upgrade facilities. And that's budgeted for 2026 design and 2027 construction. And then currently I'll just talk through cost, and then I have a good map we'll just look at. It'll probably make this a little clearer. But State Street Phase 2 uprate is budgeted right now for $1.2 million. And the State Penn gate upgrade is budgeted for $2.98 million. And then we can look. So this is what we're looking at. So in yellow is the bottleneck. So that is, east-west is the 12-inch. And then north-south is the 4-inch on Linder. And then you can see right here, this is actually Boise 2 and the State Penn gate. We kind of have two names for this gate, but that's the gate. And it runs down State Street. And we're seeing a lot of growth in North Boise that kind of supports, and in East Boise that this line feeds. And then I'll show, so like I said, we kind of built on this one. So a couple years back, we did the State Street Phase 1 uprate, which is in blue. And then you can see the next phase, as required by growth and demands, is the second part, is uprating this next section up to 500. And it'll be 12,000 feet of 12-inch high pressure on State Street and 10,500 feet of 4-inch high pressure on Linder. And it'll get us up to a 500-pound MAOP all the way back to the gate. There's other benefits to this one. It'll provide a dual feed. So we'll loop another 500-pound system, which just gives even more capacity. Having a dual feed, you got redundancy. So just operational flexibility for us. And like I said, it's going to cost $1.2 million, and then the capacity gained is 950,000 therms a day. And it's actually going to boost our capacity by 130,000 therms a day. And we have a table at the end where we'll go through our AOI lateral capacities, and then based on the alternative, we'll show up what the new capacities are. So at the end, we'll re-hit on that, and you'll see those kind of in a table. Next up, we got Central Ada County AOI. So this one actually also doesn't require any reinforcements. It can currently meet 2030 IRP growth predictions. And just a quick update. So this had a pretty significant reinforcement with the 12-inch South Boise loop that was completed in 2023. And it included, I think it was 3 miles of 12-inch high pressure down Cloverdale. And then also the CUNA gate upgrade. Next up, I'll cover Sun Valley Lateral AOI. So this one, a little bit reoccurring, but you're in good shape if you don't need reinforcements. So it's good, but not as much to present on. We do. This one also has no reinforcements required for the 2030 growth. And it's because we just put the Shoshan compressor online. So Shoshan was completed in 2023, which is the second compressor on this lateral. So this lateral runs up to Sun Valley, and then we have two compressors. We have the Jerome compressor station and the Shoshan compressor station. And Shoshan compressors at mile marker 32. And these two compressors kind of work together to boost pressures up the lateral to meet the end-of-line deliveries that are required. So with that, I am now going to transition to Zach, who's going to cover Idaho Falls lateral. Zach's done a great job of supporting and modeling the Idaho Falls lateral. And yeah, I'm going to let him share that with you guys.
Sounds good. Thank you, Kathleen. Yeah, talking about the Idaho Falls lateral here, kind of just a brief summary right off the bat. Modeling does show that we have some reinforcements that will be required to meet the 5-year growth predictions. In the next slides, we'll talk a little bit about the specifics. In the past, we've talked about this AOI and had talked about a compressor station being needed. That compressor station is under construction currently and is expected to be operational in 2026. At the end of the 5-year, we are expecting through growth modeling to see the suction side of that compressor. And when we get to that slide, I'll talk in a little bit more detail, but the suction side of that compressor to kind of go below pressure requirements for that compressor. So that is really what the capacity limiter or the AOI limiter will be near the end of the 5-year. Just talk a little bit about how we model these things as well. Kathleen, if you want to go to the next slide, the visual of the lateral will be helpful. So this is the IFL lateral. It goes from Pocatello in the south all the way up to St. Anthony in the north. Kind of the logistics of it is we take gas from Williams in the south, and it gets pushed all the way up through these lines. Some of them are paralleled all the way up to St. Anthony. In the past, and for the compressor that is currently under construction, the limiter has been that St. Anthony pressure in the north. And something here. But the limiter has been St. Anthony's pressure. I mean, all this gas coming from Pocatello, traveling through these parallel lines to the north, feeding Idaho Falls, Blackfoot, Pocatello itself, etc. Just taking off the capacity that they need, leaving St. Anthony with a lower pressure. And that is what had justified the Wapello compressor station that need to increase pressure and push it towards St. Anthony. How we model these is we use a USM model. So for our distribution side of things, we use a steady state modeling software. It's still through the same Synergy and DNV software provider, but for these larger laterals, we use an unsteady state or a transient time dependent model, which is allows us to see how these compressors, how these larger, higher pressure lines act over the course of a day, over the course of like a morning peak in terms of gas flow, etc. And that's kind of how we model the growth on these lines and justify the projects that are needed for them. If we want to go to the next slide, we'll talk specifically about the compressor station that is underway right in the middle of the Idaho Falls lateral, between north and south. We have a compressor station that is underway right now in construction. Expected completion spring of 2026 there, but really what this station does is it takes the suction side from the south and it compresses that gas to a higher pressure so that it can push further north. And this, in previous IRPs, is what we are using to increase that pressure in St. Anthony. And it, modeling wise, does a great job of doing that, pushing that higher pressure. North of here, we do have parallel lines that go quite a ways up to Idaho Falls. At a certain point, it does drop down to just a single feed north of Idaho Falls up to St. Anthony. But even still, with this compressor station, getting adequate pressures up north in the system. So just wanted to touch on this one, as I know we've talked about it in previous IRPs, is expected to be complete next year. and we'll be supporting those pressures going north of St. Anthony. The next slide, if you want to go to the next one, we'll be talking about the end of the 5-year. So, if you're unfamiliar with compressors, there is a suction side and a discharge side, and there's kind of operating limits for those compressors. So, they can only take a certain inlet pressure and increase it to the outlet side of things. So what we are modeling near the end of the 5-year here is, Kathleen, can you go back to this slide? I see your Teams
Oh,
page
I'm
here.
sorry.
No,
No,
you're
you
good.
know what? I thought I was sneaky, but
You're good. What we're modeling is that the pressure on the inlet side to this compressor will drop below kind of the operating conditions required for that compressor. So, there's a limit there that near the end of the 5-year we're dropping below. So that is what we're using or needing this additional project near the end of the 5-year, and it's in a parallel, another parallel line. Bringing adequate pressure and capacity to the compressor so that that compressor can continue to pump it further up north. Kind of the specifics of this project is, I got my paper over here too with details. What we're projecting is an 8.5-mile long pipeline of 16-inch pipe, kind of going from that Blackfoot area up to that Wapello compressor. The Wapello compressor is right on the northern portion of that green line there. And really what this does, we've considered alternatives as well. Really the only way to get additional capacity and pressure to the compressor is either additional parallels, loops, or replacement of pipe upstream of that. So we extensively modeled kind of the best case scenario, and really it comes down to reducing there's a chunk in there that has high velocity of pipe currently in the models, and what this line would do is get rid of that, or I not I shouldn't say get rid of. We're planning on paralleling, but it would allow us to kind of bypass that high velocity line with a larger diameter pipeline in order to get that adequate pressure to the compressor station. And then again, so the limiting factor at the end of the 5-year is actually not St. Anthony's pressure, it's the inlet side of this compressor. So that's the justification and need for this project here. We are expecting a rough estimate of around 42 million for this 8.5-mile long pipeline. Just as a note there. Alternatives would be replacing or paralleling in a different location. This is really the best case. It gives us the best pressure at the inlet to the compressor. I did model all the way back to Williams in different sections there. And this really, does provide that best pressure increase on the inlet side of the compressor to allow it to continue to push further north. So if you want to skip to the next slide, I think we'll talk about capacities in general. Kathleen, do you want to take this or?
yeah.
Okay.
Yeah, nice job, Zach. Yeah, the Idaho Falls lateral, like that was our a lot of our work on this IRP. So yeah, Zach did a great job like supporting the USM, and we had lots of meetings, working towards all the end-to-line deliveries. So yeah, it's a pretty extensive process. But yeah, so this is the table I mentioned. This is our AOI capacity summary and timing needs. So this goes through kind of the 5 years. So from 2026 to 2030, each AOI is listed, and it kind of shows the capacity of the AOI. So a couple that we know, didn't have, reinforcement needs. So like Ada's, it just stays the same. And then you can see State Street. When we do the State Street uprate in 2026, we go up to 950,000 therms a day. And the gate really gets the same. So they're the same. It just happens the next year. And then Canyon County, there was no upgrades. And then Sun Valley, we're looking good with that, that second compressor with Shoshan. And then Idaho Falls lateral, this is kind of what Zach went over. So in 2026, when we get the compressor on, we're going to have 1,037,000 therms, as the capacity. And then, when we need that suction side project, if we get that complete in 2030, we will go up to 1,122,000 therms a day. And there's just been a lot of growth out Idaho Falls way. So a lot of LVs, core growth, just a lot of growth out kind of in eastern Idaho. And this table lets us kind of see the timing, and where you get with the alternatives. So it lets you compare a lot of things. It's a great tool. I really like this table to be able to talk about it. And then it also shows that we can kind of meet our 5-year planning needs. So when we're looking out 5 years, some of these are really large, complex projects that take multiple years, and that's why we're starting to do like design work even 2 or 3 years early, just to make sure we can get the whole project done, designed, even gate stations and things with Williams we're starting to do, in multi-years. And it gives you enough time to make sure we can construct and plan these projects to meet the deficits. And then also with this table is, I like to touch on our IRP cycle, because I think every 2 years is a great time to like do these thorough reviews. Like I said, Zach, and all the USM and, all the meetings and looking at the Idaho Falls lateral, because we really had kind of this big project come into the 5-year. So just a lot of time checking, scrutinizing that project, going through alternatives. And then we will redo that. So depending on where the actual growth happens, in 2027, our next IRP, we'll be relooking at all this. So we'll be relooking at the suction project, timing, is it correct? Does it need to move up? Or can it get pushed out? Things like that. So I like this table too, and it just kind of shows our iterative process every 2 years, these nice thorough reviews, to show that we can, that we're planning everything out, loading in growth. Yeah, and that's what I got. So that kind of concludes us. I think we got questions after this. But yeah, Zach and I, that kind of concludes our part of the presentation. And yeah, we're available to answer questions.
Can you explain why the State Street gate upgrade doesn't increase the capacity?
Yeah, I can. So it's kind of already, so it's limited by the uprate capacity. So when we do the uprate, really, I mean, you're right, probably the gate, could have endless capacity, but what you can actually get down is limited by the piping. So it's limited by what the uprate is. So we just put it in the uprate capacity.
Okay, thank you.
Yeah. I mean, I could see that you could, subjectively go 2 ways on that too. But I didn't want to confuse it because it's the AOI. So it's the AOI capacity, which is why, the physical capacity of the gate probably is higher, but it's limited by the pipe, right out of the gate. It can only flow so much.
That makes sense. Thank you.
Yeah, hopefully.
Sanjay has his hand raised as well.
Yeah.
Maybe not, I guess.
I just saw Russ's hand. There's a couple hands flashing, but
yeah, Sanjay, did you have a question?
I'm sorry, sir. I turn on the mics. Yeah, I have a quick question about the designing of the capacity. So when you design the capacity of the distribution line, I think some target year is required for the forecasting load. So I'm curious about what target year is the designed for the designing of the distribution line.
So we can talk through that, and Zach, feel free to help anytime. But we go through each year. So when we get our 5-year growth predictions, we have growth for each year, and we get that from Brian's team. So we look at it, and usually how I'll approach it is I'll jump ahead to the 5-year growth, and I'll see if it can meet that. And if it can't, then I'll go back year by year and kind of do iterations to figure out when the timing is.
Yeah.
So the capacity, oh, go ahead.
Yeah, my question is initially is the designed some distribution line size. Yeah, you have to decide the size of the distribution line. So I think the it requires some specific load data to design the distribution line size. So what target year is the further designing, initial designing of the pipeline? So
I might be able to touch on this a little bit. I think maybe your question is like how we are determining those final capacity values for the AOI. Is that correct? I mean, I understand you're talking about the years. I mean, we would get our 5 years of growth data and model those individually. But then we also are able to ramp up the models beyond that growth, if that makes sense, beyond the 5 years. And that's how, I mean, we can't determine, what year it is beyond that because we don't have that data from Brian's group. But I mean, we can ramp up those models to see what the physical limitations would be in the future, if that makes sense.
okay, I got it. So yeah, 5 years data is required per compared to the okay. Thank you.
Yeah, so we make sure I guess I'll just touch a little bit. I think we got it. I think we're on the same page, but we ramp up to make sure we can meet the 5 year. And then we have certain design conditions that limits the deficit. So whether it's like an end of line pressure or physical capacity, there's a couple things that tie into those AOI capacities. And we normally ramp up and we just try to get the total capacity where we're still in our engineering design criteria. So on a lateral, it's the easiest one. So if your St. Anthony's pressure on the Idaho Falls lateral needs to be 100 pounds, we can put a load out there and we can tell you how much total we can flow through it, and be at 100 pounds, at the end of line pressure. Does that make sense? You were asking, but we don't know necessarily when that target year is because sometimes, some of these reinforcements, like a compressor, you want to plan for more than 5 years. Arguably you want that to last for, 10 or 20 years or something like that. You don't want to oversize things, but you want them, within reason where you're getting kind of a good price point. The sweet spot, I guess, is what I would kind of call it.
Yeah, actually, so I am a water engineer, so per the designing of the water treatment plant. So yeah, it's normally the water treatment plant forecasted the 20 years demand and then designed for the 20 years demand. So yeah, so I'm curious about the gas section is designed also is 20 years forecasting. Yeah, so yeah, but you already mentioned is only 5 years is considered for the forecasting. Yeah, that is fine with me. Thank you.
Yeah. We have to be careful because we get pushback if we over design. So there's kind of that, like I said, that sweet spot where, yeah.
Great, thank you. Russ, did you have anything a question or something to add, or are you good?
I'm good, Brian. It was an unintentional hand raise. Thanks, though.
Okay, no problem. All right, thanks, Kathleen and Zach.
Thank you.
Yeah, we'll go ahead and take a quick 5-minute break, and we'll come back 2 minutes after the hour, and we'll finish out this presentation. Okay, we'll go ahead and get started again. I need to reshare my screen. Hopefully everyone can see that. Okay, so I'm going to go ahead and discuss IRP optimization model. So what we have now is we've basically gotten to the very end where we're discussing the optimization model in terms of Plexos and the system enhancement. So I guess you could probably shade that in blue about halfway. So we've discussed the system enhancements on the company's distribution system. And now we're going to talk about enhancements or not alternatives, but incremental resources on the upstream side. So the IRP optimization model, this is where we integrate and coordinate all the main functional elements of IGC's operations. So we take our our load demand curves, our demand side management, our storage facilities on the upstream, our storage facilities on our distribution system model. We consider our transportation on the upstream, and then our distribution system physical capacity flow. So again, load demand curves. We also consider gas supply, from where it comes, how much, what price. So we have the price forecast. Gas transport. So we build in all of our transportation contracts from their receipt point, so where they come from, all the way down to their delivery point where they go. Demand side management, that's the cost-effective energy efficiency projections, which go in and in the Plexos model. So previously in the send-out model, they would go in as a free supply to a certain area. But now it goes in as a decrement to demand. So it's a lot more clear in this model how it's being implemented. And then local gas distribution. So this is the local sizing that that Kathleen and Zach just talked about, and we build these into our model as well. And then so like I had mentioned, we use Plexos, which is a linear optimization model, and it determines the least cost manner to have loads served by supply, transport, DSM, and laterals. And all results presented here are draft and subject to change. So just wanted to point that out. So what is optimization? So again, Plexos uses a standard mathematical technique called linear programming to optimize over all possible combinations. So it looks at every single day and it tries to optimize it as best as possible. So the model, one thing to keep in mind about these models, and this is what the analyst has to keep in mind when looking at Plexos, it does know the exact load and price for every day, so it may be able to minimize costs in a way that would not be possible in the real world. So if it knows that prices are going to increase the next summer, it may not try to cycle as much storage. So this is something that we have to keep in mind. It does have perfect knowledge. And again, we use Plexos as a tool. We do not use Plexos as a decision maker. We analyze the data that comes out of it and make decisions based on it. But we also have to make sure we understand all the different quirks about the Plexos model and all the different results. It does select the a mix of resources over the planning horizon to meet forecast loads. So what are the functional elements? Demand forecasts, so the load demand curves, areas of interest, traditional supply resources, the existing and potential gas supply basins, storage resources, and then transportation capacity resources. And then there's the price forecasts, and then non-traditional supply. So new distribution capacity, RNG is also considered in DSM. So again, here's the map of the pipelines. So this is kind of just showing the actual pipelines at a high level, all the different pipelines. And I'm going to kind of compare this to what Plexos imaging looks like. So it's not exactly perfect to what these maps are, but you can see how we have this set up. So you can see that we have Sumas over in that top left, the very northwest, and it does feed JP, so our JP storage, and then there's capacity, transportation capacity out of JP that can go to Intermountain. And then you could see I had to the imaging from Plexos is still very early stage, and so when I zoom to get that ACO up in the very top into the image, I had to zoom way out, so that's why it's cut off there. But the ACO right above Calgary, it goes to ABC, goes to Kingsgate, and then it goes down to Stanfield. And the cool thing about Plexos is you can geonode, so you can put a longitude and latitude for these in here, and it maps it to its exact location. Now it doesn't really do much for the actual model, but it does help when looking at the images. So you can see Opal down there in the Wyoming area, and it feeds Intermountain from the south. And then you can see how we have our different areas of interest broken out. And then you can see I think the Rexburg gas facility is actually in the wrong spot. So that'll have to be moved. But that's kind of the zoomed out look. When we talk a little bit about each of these different aspects, so here's transport. So you'll see these blue lines. When you look at individual areas and zoom in a little bit further, you'll see that there's more than just one contract. So for example, we're zoomed in on ACO to ABC. So this would be our Nova transport, and there's 4 different contracts on here. So that's why there's 4 different arrows. That kind of arrow, so the way that it's pointing is the way that the gas is flowing. So you can have, if a pipeline is, so if I go back a slide, so like Northwest Pipeline, you can flow south to north from Opal up to Intermountain. You could also flow north to south, so Stanfield down to Intermountain. And so that's how those are built in. You can look at the map, make sure everything is pointing in the right direction. So just to talk about transportation, this is the means of how Intermountain gets gas from the supplier to the end user. There's an MDQ, a D1 rate or a reservation charge, a transportation rate or a flow charge, and then a fuel loss percentage. So the MDQ, that is the maximum daily quantity. So that's the maximum we are allowed to flow on that contract on a given day, and we can be held to that number. So that's the number we put into the model as our maximum amount. The D1 rate, this is our reservation rate. You can kind of think about a D1 rate as like a paying rent. So whether you use it or not, you have to pay rent on it. So you have to pay for that contract to have the right to move gas. And then the transportation rate is if you do decide to transport gas, there's additional cost tied to that. So that's the transportation rate. And then fuel loss percentage. So there's a statutory percentage of gas based on the tariff from the pipeline that is lost and unaccounted for. So we put that percentage in. That way the model knows if we want 10,000 decatherms at ABC, we might have to buy 10,700 decatherms. So just so the model knows that and it can account for having to purchase a little bit more than it needs. So storage, this is how storage looks in the model. It has these purple lines to show that it's connected. So it's not really a transportation contract between this Plymouth Interconnect and this Plymouth 1, 2, and 3 contract. The purple line is just showing that these contracts are connected to this node, and then any transportation contract in and out are connected to these storage contracts. Intermountain has 5 locations: Jackson Prairie, Plymouth, Clay Basin, Nampa, and Rexburg. Storage injection targets are set at 35% by the end of June, 80% by the end of August, and 100% by the end of September. And this is to kind of just show what cycling storage is for needle peaking. Intermountain can withdraw approximately 30,000 from JP, 155,000 from Plymouth, and 70,000 from Clay Basin for a total of approximately 255,000 decatherms per day of off-system storage. Now, obviously, those have a maximum capacity as well, so we have to optimize, like Ryan had mentioned, our storage and make sure that we have that amount in there throughout the winter period. If we cycle our storage and we're empty by mid-January and a peak event happens in beginning of February, we wouldn't have enough storage to serve that. So we have to make sure we optimize. Again, Plexos has that capability and it allows us to review that and look at what Plexos does to optimize, and how much it still has at the end of January is good information for the company. And then Intermountain can withdraw approximately 50,000 a day from Nampa and 5,500 per day from Rexburg for a total of 55,500 of on-system storage. So for supply, this is the very end point or the starting point, the receipt point of where the gas comes from. So at this point, you can purchase the gas. So we have ACO, Sumas, and Opal. And then we also allow the model to buy a little bit at Stanfield. Now, Stanfield's not very liquid, so it's limited to a very, very small amount. And it also bakes in the price of transport. So if you were to buy Stanfield, you're probably buying gas at a price of ACO plus what it costs to transport the gas to Stanfield. And there may also be a little bit of a premium in there as well. I'm actually going to jump over this, or actually I'll cover this real quick. So we have a base, a winter base, summer, winter day gas, and peak day incremental, which I'll talk about on the next slide. And then the contracts are renewed in November and April. So the season long ones are done every November, and then the 6-month contracts are done November and April. And so this kind of breaks down how supply is purchased within Plexos, and it kind of falls along how Eric kind of buys gas as well throughout the year. So there's generally a base supply that will serve that annual load no matter what, and it's considered a must take. So we must take it. So what the model does is it optimizes it and says, here's what we know we're going to need all year. We're going to buy these contracts knowing that we're going to need them, but we're not going to buy too much because when we can't take it, we don't want to have to pay for that gas. And then there's winter supply, so the period from November to April, where again, it's a base amount. We know we're going to need about 140,000 decatherms. So during the winter, we're going to increase that supply, that base supply that we're interested in. And then winter day, you can see the yellow dot dashed lines. So this is day gas that we buy during the winter. And then the green is the day gas we would buy during the summer. So this is day-to-day gas that we might have to buy. Let's say Eric sees a cold event coming, but it's not like a peak event, and it's above what our base can cover. He'll go out and purchase that. And so that's what we call day gas in here. And then peak event, that's when it's extremely cold. There's a little bit more of a premium on that price of gas. And so that's how it's modeled in Plexos. And then demand areas. So again, I think we've mentioned this probably about 30 times throughout all the IGRAC meetings. But we have 5 areas of interest and all other. And so you can see how those are tied together. There's actually an imaginary line between each of these, the core and the non-core, because on the distribution system, they're tied together, but on the upstream side, Idaho Falls, all these different areas of interest on the transport customers, they end up buying their own gas and transporting their own gas. So we don't track the cost of those in our model. So like the IGC non-core, we just put free gas in here because those customers are in charge of purchasing their own gas. We put free transport in here because they're in charge of paying for their own transport. But to understand if we have any capacity constraints, we model those in here and we constrain these together. We say you can flow, I don't remember what the Idaho Falls numbers are here, but just using 100,000 as an example, you can flow 100,000 to Idaho Falls, so you can flow it to here, or you can flow it to here, but the sum of those cannot exceed 100,000. So this is just another way that we can track and make sure that we are getting enough physical capacity on our distribution system. And then, yeah, draft model results. So this is just another way to look at our load demand curves. And this, so we had shared our 2025 and 2030 up above. And this one kind of shows every single year. So this is 2025 to 2027. Again, like Kathleen had mentioned, there's been a lot of upgrades already done. And so you could see the planned capacity upgrade. The percent of existing capacity before those upgrades, you can see we're up in the 90%. So one of them was at 100%. So we were very much at the maximum, very close to hitting our physical capabilities. Those upgrades have helped a lot, putting us in the 70s, 80s% area. And so this one includes the capacity upgrades that I believe have happened already. I think we may have included one a little bit too early. I can't remember which one it was. You can see here that the models look pretty good. It does look like Central Ada without an upgrade, which I'll talk about in a couple of slides, is at 101% in that final year. So again, just to recap, these are distribution system shortfall solves and recent upgrades that Kathleen and Zach have talked about. So a lot of good information coming from their presentation, and really important upgrades that they've done on our distribution system. On the upstream side, we're looking at transportation shortfalls. So if you recall from Ryan's total system load demand curves, there was a shortfall. So we're looking at a Rockies connector, and we're participating in that. We're also looking at renewing contracts, as well as alternative transport uptakes. And then again, renewable natural gas is a consideration. And then obviously, if there's any others that you guys want us to consider or think about, we're happy to do that as well. So now this is the laterals with the upgrades post 2025. So any upgrades after 2025. So you see the State Street upgrade that got put in there. And then the 2900 from that suction project that Kathleen and Zach were talking about. And so you can see, based on all these capacity upgrades, that the company is in a much better position to serve its customers in a design event. Are there any questions so far? Yeah, I'm not seeing any. So I'll go through this real quick. So this is a draft model result to kind of show how the company is getting its gas. So you can see a lot of gas is coming from the ACO area, probably in the 80 to 90%. And then there's gas coming from the Rockies area, and then some from the Sumas area. The Sumas area helps fill up the Jackson Prairie storage facility. And so you'll see that being heavily utilized in the summer months, or in the spring months. Same with the Rockies. Rockies is utilized to fill up Clay Basin. So you could see that it's being heavily utilized in the spring as well to serve demand, or to fill up storage. And then the green, that's the demand side management. So you can see the DSM amounts that are going, that's total DSM for the month. And these values are in decatherms. And then you can see when storage is being utilized. So this is storage withdrawal. And you can see that it's mainly being utilized in January because the peak, the design event we have peaking. If you think back to the low demand curves, that peak event is happening on January 15th. That's the way that Intermountain's always modeled it, kind of later in the winter period. But you can see how storage is being utilized all the way into March. So this is the first year of the planning horizon, 25 to 26, and this is 2030, 2031. Again, similar look. This one's utilizing a little bit more Sumas. And then we have a lot of ACO and a lot of Rockies. And then again, DSM is cumulative, so you'll see that number increase over the planning horizon. And then storage, those numbers don't really increase because the amount of storage we have is fixed over the planning horizon. We don't have any plans to increase the storage as of right now. But if you pull these numbers and look at the amount coming from the supply areas, those would be increasing just because the demand is increasing. And then here's a model result on peak day supply. So it's a little difficult to see when it's zoomed out this far, but we have a demand line and demand less DSM. So DSM, when looking at it on a peak event, on a single day event, it doesn't have much of an impact. It has more of an impact when you look at it on an annual basis. But a lot of peak day is served through ACO. That's where most of our transportation's coming from. That's where the cheapest gas is from. A little bit from the Rockies. There's a little bit from Sumis, and then storage is the light blue. So a lot of ACO, a little bit of Rockies, and a lot of storage to meet peak day. So capacity resources. So again, we have about 224,000 from Stanfield, 59, about 60,000 from Rockies, and then we have a Citygate deal of about 10,000 for a total capacity of 293,000 decatherms. And then the storage withdrawals, so 155,000 that's with bundled capacity. So bundled capacity is with transport. And then JP TF2 capacity of 30,000. And then Nampa and Rexburg. So the total amount that the company could deliver to the system is about 535,000 decatherms. Something that Intermountain did a few years back, and it was discussed in the previous IRPs, is the company has segmented capacity from Sumis to IGC at Stanfield, and Intermountain owns the Stanfield to IGC piece. And then the company added Stanfield capacity via the West Path project, the GTNX project. And this gets more of that cheaper ACO gas. And currently, Intermountain is actively participating in a Rockies expansion to meet peak day shortfalls. And that shortfall, that number is still being determined. It'll be part of the IRP, the final narrative as to what Intermountain is seeking. And then on-system storage is about 55,000 decatherms a day. Are there any questions? Okay, not seeing any questions. So just to wrap this up and summarize it, the company employs utility standard practice methods to optimize the system. We model DSM storage, withdrawals, injections across the entire season. And ultimately what this does is it provides a check on the need for lateral expansions on our distribution system. And then it provides a check on transport and supply and demand storage resources. So if we need more resources, this provides a very good check for that. Are there any questions? Yeah, Sanjay?
Yes, I have a question about the modeling. So, yeah, I believe the in the consumption in other state is so important to decide the capacity, because you already show the map is the line is connected to the from the Calgary in Canada to Utah area. So I think there is some consumption in other state, in Washington, Oregon also. So the consumption is the impact to the capacity in Idaho distribution line. So I wonder is how to consider the other state consumption in the model.
Yeah, that's a good question. There's a lot of different ways to look at this. So one thing that I think we need to keep in mind is that the company does have these contracts that the pipelines are required to meet. And so having those contracts and knowing what they're required to deliver helps us not have to worry too much about the other states' consumptions. Now, when it comes to actual operating, like what Eric does, yeah, he definitely has to consider consider these constraints, operational flow orders, things like that. So it's definitely on the operation side. There's a lot more to consider on the planning side. When for contracts that are already in place, I think there's more certainty around what we can flow to our contracts. Now, when it comes to incrementals like the Rockies connector, there's obviously going to be other people, other entities interested in that capacity. And so, yeah, that going out and getting incremental capacity, there could be a little bit of demand there from other entities on it, which could impact how much we can get, how much we should consider. So yeah, there's definitely consideration around the other states and how they impact us. But from a planning perspective, there's a little bit of certainty around our contracts. I don't know if anyone on the gas supply side has anything further to add to that. And hopefully, yeah, go ahead.
Well, yeah, I'd say Eric might be the appropriate person, but I think your first point is addresses that the most straightforward. It's we have that reserved capacity. We're we pay for that. IGC customers, ratepayers pay for that capacity every day. The pipelines have tools to make sure that nobody else takes our capacity. They keep their systems balanced, and we do that multiple times a day through the nomination process. So from that, we can't expect to get what is available shipped to us every day, even on a peak day. So if others are taking too much, then the pipelines will have tools, entitlements, financial penalties to those folks that are taking too much, more than their fair share, to help limit that, to make sure that IGC customers get the capacity that they're paying for. So I think that's kind of the main point to keep in mind.
Yeah. Thanks, Chris. Sanjay, did that answer your question?
Yes, that is helpful to understand the modeling. Thank you.
Yeah, no problem. Okay, are there any other questions? Are there any questions for one of the earlier presentations that the question just popped up now? Feel free to ask those questions now. If there are no other questions, I just wanted to remind folks you can reach out to us at the irp.comments@intgas.com. If you have any questions or if you want to provide feedback or comments, please do so. We'll try to implement any comments or feedback within 10 days into the IRP narrative. If you have any questions, if you just want to have a clarifying question, we're happy to take those as well. Any form of communication is great. We're also happy to jump on a call if you have multiple questions and would just rather talk through it. We're happy to do that as well. So we are available. So please feel free to reach out to us. With that, I didn't put a slide together, but this is the last IGRAC meeting, and we will be putting together the narrative over the next month and a half, and we're aiming for the end of October to wrap up narratives and provide that out to the group for a draft. And we would be happy to take feedback on the draft, and then we'll wrap up the narrative to file in December. So those are the next steps for the integrated resource plan. All right, so I'll open it up one last time for questions. If I don't see anything within like 10 seconds, we can end the call.
Thanks for all this great information. Appreciate it.
Yeah, thank you. Yeah, thanks everyone for joining. I really do appreciate it. And the questions, those are great questions and excellent conversation. Thanks everyone.
Thank you.